Yeah, for electric fields, I'm going to review a little bit the gravitational field, which we're familiar with, even though that word may or may not have been used. So here is what I'm going to remind you of, to just motivate why do we care about this thing called electric field. So let's forget about electricity for now. So you know, if you have two masses, here is Earth. Let's say this is the mass of the Earth, capital M. And then you have an object near Earth, little m, right? And the distance between them, let's say this is the radius of the Earth. Distance between them is the radius of the Earth. So we know the gravitational force, Fg, G for gravitation. This is just a review to motivate why do we want to do this electric field thing. So the force between two masses, the magnitude is G. The first mass, which is capital M, and then little m, divided by the distance between them squared, which is the radius of the Earth squared. You're near the surface of the Earth, so it's basically the radius of the Earth, right? So this piece of chalk, how far is it from the center of the Earth? It's the radius of the Earth plus this much. This much is negligible, so it's about the radius of the Earth. Okay. So that's that. This is good, right? Capital G here is 6.67 times 10 to the minus 11, the gravitational constant. And here is the mass of the Earth, here is your mass, and this is the radius of the Earth squared. Now we know F equal to ma, so the force is equal to the mass times acceleration, so we want to figure out what our acceleration is. Right? F equal to. So if you do this, we're going to cancel this. We get A will equal to capital G, capital M over R squared. Okay? So let's use some numbers and to get familiar with this equation. The numbers are, we said G is what? 6.67 to the minus 11. What's the mass of the Earth? It's about 5.98 times 10 to the 24 kilograms. That's the mass of the Earth. And then the radius of the Earth? About 4,000 miles, right?
Yes.
6.38, I think, times 10 to the 6 meters. And we need to square. So let's please plug in these numbers and see what we get for A. Yeah, but let's do it. Suppose you don't know. So we want to actually do it. Yeah, good for recognizing it.
9.79.
All right, so about 9.8, good. One person at least did it, so we get meters per second squared, so it's G. That's called the gravitational, acceleration due to gravity near the surface of the Earth, or we can also call it the gravitational field. What's the advantage of this? Notice, if I know G now, I know the force on any object. Let's say I have this piece of chalk, it's mass M. What's the force on the piece of chalk? mg, right? mg. So whatever the mass is, if I have this eraser, it has a different mass, but what would the force on it be due to Earth? mg. So just multiply the m by the g to get the force. So notice, it's basically the gravitational field is everything shows up except for the second mass, that other mass. So everything shows up except for the second mass. So the force would be this, the mass times the gravitational field. Right? Mass times gravitational field. M times G. G is due to Earth. So the Earth's mass generates the G. Right? It produces that gravitational field. And then who experiences that gravitational field? Another mass, the other masses, somebody else. The mass that's placed on that gravitational field. So, which is to say, the mass times G, right? At least near the surface of the Earth is going to be 9.8. And you get that. So F equal to mg. Very similar thing to the electric field. When you have two charges, instead of having two masses, one charge produces what's called the electric field, and the second charge will experience that electric field. Okay? So here it is. For two charges, the force from 1 on 2 we said is K Q1, Q2 divided by the distance between them squared, and then R hat, right? R12, R12 hat. Clear? Now I can rewrite this as, I can put Q2 times everything else, which is K Q1 over R squared, and then R hat, right? What's the difference between this and this? No difference, it's the same thing, so F. So this part here is called the electric field, E1. This part is E1. So E1 is equal to K Q1 over R squared R hat. So E is the electric field produced by charge 1. Electric field. Charge due to the charge Q1. So let me here. What are the units? The electric field. What would the units be? Huh? Yeah, if you solve for E, you get F over Q. So newtons per coulomb. Yeah, so the units are newtons per coulomb. In 2 chapters, we will learn about the volt. So I was just want to write it. They can be written as a volt per meter. I know we don't know the volt yet, but that's okay. I just want to mention in case when you see it in the future, it will make more sense. So they're equivalent. For now, we use the word newtons per coulomb. In 2 chapters or 3, we will use the units volts per coulomb. But they're equivalent. Okay, so let's say electric field due to charge 1. We found the units of it. Okay, so we want to get familiar with the electric field. So notice, by the way, for the electric field, it's newtons per coulomb, force per unit of charge. Electric field is force over charge. The gravitational field was force over mass, right? F over m would be G, right? So G would be the gravitational force over mass. So force per unit of mass, newtons per kilogram, is the gravitational field. The electric field is force per coulomb, force per unit of charge. So that's the analogy. And that's why we care about the electric field. Our job then will be this. Find the electric field. Once you know the electric field and you place, so let's say the electric field is known to you everywhere in space. Now you bring a charge Q and place it in that electric field, and someone asks you, what's the force on Q? Well, it's whatever the electric field is at that point times the charge. So just whatever charge you place in the electric field, just multiply it by the magnitude of the charge in the electric field, and that's your force. Okay. Electric field is what's called a vector field, not a scalar field. So a scalar field would be like this, like temperature. What's the temperature everywhere on Earth? It would be, let's say, at this point, there is a temperature. But it just has a magnitude. Every point in space has a particular temperature, right? So it's a scalar field. A vector field would be like the wind. Every point in space has the wind. The wind will have a particular velocity, so it will have a certain direction, a certain magnitude. So everywhere in space, for the vector field of the electric field, it would just be, every point in space would be assigned a particular magnitude and a direction. Yes?
It's interchangeable, like if we do force like 2 applies on 1, does it have to become a charge of 1?
Yeah.
Like through the field?
Yes. Yeah. So if you switch, if it will be the force due to 2 on 1, yeah, it will be completely symmetric. So we just, if you switch these, then you have Q1 and here E2. But let's focus on charge 1 for now, and then we will worry about multiple charges in a second. Yeah.
What if you wanted to use the electric field for charge 1 to find the force on charge 3? Would that R still be there, or would it be a different R?
So you would figure how far, so you have to find the electric field due to charge 1 at the location of charge 3.
Oh, so this
Yeah.
is an electric field at 1 point space. It's not like the
It's,
actual field yet. Right?
It is the field, right? Because R will have different values depending on how far you are. Yeah.
Okay.
So let me draw the field and see what happens. Let's get familiar with it for positive charges, negative charges, and then we'll use it to make some calculations, and then we'll see how we can calculate the field. So it will be more and more maybe clear. So here is a positive charge. Let's start with a plus charge. Here is a positive charge. This is positive. And I want to know, let's say I'm a distance r away from it. Here is a distance r away, right? As long as I'm a distance r away, I'm on a sphere, right? Right? So this is the charge. If I want to be a distance r away, I can be here, I can be here, I can be here, anywhere on the charge. So here's what the electric field says, or the electric field equation says. The magnitude of the field is this, K. K is a constant, it's 9 times 10 to the 9, so it's a positive number. How about Q? If Q is positive, then Q is positive. And then R squared is always positive. So this would be a positive quantity, right? If the charge is positive, this would be a positive quantity. R hat. In what direction is R hat? Huh? Away. So it's just away. What does away mean? Well, it means this. If I'm here, away means this way. If I'm here, away means this way. And so away, radially outward, is this way. Okay? And then that's away. Okay. So the direction of r hat is just away. Okay, that's the direction of r hat. It's just radially outward. Now, if I multiply a vector that points radially outward by a positive quantity, what happens to the direction of that vector? Nothing. Yeah, it just makes the vector longer or shorter, but the direction is just outward. So we say the electric field points away always from plus charges. So the plus charges, we say they are the source of the electric field. They always create an electric field. The electric field always points away from plus charges. Let's see what happens if you have a minus charge. Here's a negative charge now. Let's say we're a certain distance away from it. I always draw a sphere because a sphere would have a fixed radius. So here it's the distance r, here it's the distance r, here it's the distance r. So now, let's think about what happens to the direction. K is a positive number, r squared is a positive number, but Q is negative. It's a minus charge. So what happens when I multiply, this would be an overall negative number, a number that has a minus sign times a vector. What does it do to the vector? Reverses the direction. Good. So the direction is going to be this, the electric field, right? So the direction of the electric field due to these, due to a minus charge, it just goes toward the minus charge. So electric fields, they start from pluses and they always terminate or end at minus charge. They always point toward the minus charge. Another thing about the magnitude of the electric field, the farther away you move from the plus charge, the smaller the electric field, right? Because R gets bigger, so the electric field gets smaller. The farther away, the smaller the electric field. So for example, if you're here, the electric field has this size, then if you're here, the electric field will have a smaller size. And if you're farther away, maybe the electric field will have this tinier size. So the farther away you are, the electric field will have a less and less. So to answer your question, if I were to place a charge Q3 here, right, the force on it will be whatever the electric field is at this point times the charge. And if I were to place a fourth charge maybe here, the electric field would be in this direction, and that, so whatever this charge is times the electric field. So if the charge is positive, the force will be this way, meaning repulsive. If the charge is negative, this vector will flip and then it will be attractive. So the importance of the electric field is once you calculate it, the force is trivial. It's just whatever the charge is times the electric field that gives you the force on the charge. So it enables you to do things. The advantage is for forces, how many charges do you need to talk about the force?
Two?
At least two, yeah. If you just have a single charge, can you have a force? It doesn't apply force in itself. But what does it do? It produces an electric field. And that electric field is waiting to be experienced by another charge. Okay. So our job now will be, we will mostly be focusing on the electric field. And we will be calculating the electric field for different configurations. We will talk about electric fields for single charges, 1, 2, 3. And then we'll talk about electric fields for just two oppositely charged things, like we call it a dipole. We'll talk about that for a little bit. And then we'll focus on continuous charge distributions. And that will involve some integration that will be for next time. And then next week, after the test, we'll be focusing on Gauss's law, which is also how do we calculate the electric field in more, when we have symmetry and we got more complicated situations. So the next couple weeks are about electric fields and how to calculate it, basically. Okay. All right, so another thing is, so I think I mentioned that, if you have more than one charge, how do you find the total electric field due to all the charges? If you can guess, yeah, you would add them. So the electric field due to charge 1 and 2 and 3 would just be the sum, E1 plus E2 plus E3 and so on. So let's do an example here for a single charge, and then we'll do multiple charges and then see where we can get. So here is this charge. Here is the X, and here is the Y. And let's say I have a charge here, and it's minus. Right? This is negative charge. So Q is equal to minus 1 nano coulomb. Nano means 10 to what power? So minus 9, right? So that's 1 nano. We would like to know what's the electric field at this point, at point 1. What's the electric field at point 2? Okay? And given that this distance is 0.02 meters, and this distance is 0.02 meters. And it's a square. So find the electric field E1 and E2. Here E1 is, they're both fields are due to the same charge. They're called E1 and E2 because they're just different locations. Okay. So which electric field is going to be stronger, at 1 or at 2? At 1. So let's start with 1. Let's find E1. It's actually, I think it's easier. So here is E1 will be what? What's the definition of the electric field? KQ over R squared R hat, right? So I'll put here, K Q over R squared and then R hat. Or I can use the cubed one also. I can use the K cube, and then vector R over R cube. In this case, is it easier to use the R hat or the one with the vector R? R hat, why?
Only
It's along the Y direction, yeah.
J direction.
Because the unit vector, the unit R hat, in this case, here's R hat. In this case, R hat is just J hat, that's all. That's the unit vector that points away. So, so 9 times 10 to the 9. Probably need more space. And then 10 to the minus 9, right? For this one, or negative. And then how far are they? Or how far is that point? 0.1 from, sorry, 0.02. So 0.02 square. So 10 to the minus 9, 10 to the 9. So it's going to be yeah, I need help with that actually. 225? 225?
Yeah,
Two more zeros. Okay. And J hat, right? And the units are units per coulomb. Good. I'll put the units this time. So does it make sense that the electric field points in the minus J hat direction?
Yeah.
Yeah, it's a negative charge. Electric fields always point away or toward negative charges?
Towards
Towards. Yeah. So the electric field is, in fact, ends up pointing this way. That's E1. Okay. Now, for the next one, at point 2, R hat at point 2, here is R hat. R hat points this way. Is that a nice unit vector, or it's like, yeah, it's not so nice? So we probably will use which one? The cube,
R
right?
vector.
The one with an R cubed at the bottom. So I get this. E2 will be K cubed, and then R cubed, and then the vector R. So I get K, 9 times 10 to the 9. This one is minus 10 to the minus 9. Very good. Oh, how far? What's this distance?
Square root
Square root of 2 times A, right? Which is 0.02. Right? Times 0.02. The diagonal. So we got this. I'll just write root 2 times 0.02. Like this to the 3. And then what's the vector that points from here all the way to here? 0.02 I hat plus 0.02 J hat? Yeah, correct. So it would be 0.02 I hat. Good. And then 0.02 J hat. So let's get that. So we get E2 would be something I had, and then something J had, or the same thing J had. It would just both would be good. Don't have the answer.
It's gonna be minus 7954.95.
5.4?
Yeah, 0.95.
0.95? I'll put 5. Like this?
Yeah.
Thank you. And then the same thing here, right?
Yeah.
7955? Yeah. That's it. That's good enough. And that makes sense because vector E2, the electric field at position 2 would be pointing away or toward the charge? toward, yeah, so both the I hat and J hat are negative, so it's towards. So here's what's the magnitude of E1? How much is E1? So this one, right?
Yeah.
22,500. What's the magnitude of E2? Let's calculate it. We should do it. This squared, add them, take the square root. Just want to compare them.
11 to 15.
Would be half, right?
Yeah.
So just, so you said 11 to 50?
Yes.
Newtons per coulomb. Yeah, that's the value. So you can just square, take the square. Yeah. Yeah.
What's the value of Q?
Q. It's one, negative 1 nanocoulomb, so negative 10 to the minus 5.
It's, oh, okay.
This one.
And then, my second question is like, why one of them, like, they were both negative, like, the values were negative and they were both like,
Yeah.
two. Why?
You mean why is there a negative sign in front of it?
Why it's the direction of the vector? is
Oh,
not-
okay. So let's draw this vector. It's a vector, it says it has this much in the minus I hat direction, so the vector has this magnitude, right? It has this component, and it has this component in the j hat direction. So overall, the vector is this. Okay.
Thank you.
Yep. Okay, the next topic is going to be multiple charges. What's the electric field if we have, let's say, 2 charges or 3 charges? What will the electric field be? And I'm going to, so here is Q, 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 G. I'm just trying to write the example that's exactly the one I have in the notes. So here is the x-axis. This is our next example, okay? Let's say I have a charge. Here is charge 1. And it is Q1 is just Q, okay? And it's positive. You can assume it's just Q. Okay? And charge 2 is going to be here. So Q2 is also going to be given a value of Q. We're going to work with symbols in this example. And then Q3 also will have a value of Q. Okay? All 3 charges have a value of Q. And the distance between them is going to be D or A. Yeah, let's call it D this way. From here to here it's D. And from here to here is also D. Both of these are D. And we would like to know the electric field at point P. We would like to find the electric field at this red point here. It's the electric field at that red point. And that red point is going to be, let's say it's a distance, let's call it X. So find the electric field here at this red point. So let's start with this positive charge on top. And we will do it qualitatively and then we will do it analytically. So qualitatively, in what direction is the electric field due to charge 1 at this point? To the right, like this, down? It's a positive charge, so it produces electric field away from itself. So draw a line from the charge to the point and then go away from the charge. So it's this way, right? That's E1. Electric field from charge 1. Let's do E2. Electric field due to charge 2. In what direction? Just horizontal. Yeah. So this is the charge. Away is that way. So it's going to be like this. going to be E2. You know why I drew E2 to be longer than E1?
This is
It's closer, right? E2 is, E1, 1 is farther, so it will be weaker. Let's go to 3. What direction?
Northeast.
Northeast, you said? Yeah, this way? Yeah, that's E3. So in what direction, if I add all these 3 vectors, in what direction is the net field going to be?
Horizontal.
Yeah, to the right. Yeah, it's just gonna be to the right. Yeah. Because you see E3, it has a little component this way. So does E1 though, but this way. And since they're equal charges, same distances, these we expect them to cancel. And so overall, the total electric field should just have an X component. It should not have a Y component. So we already know the answer. And so now when we do the math, we should match our expectation. So that's what we're going to do. So here is vector R1. Who can tell me what vector R1 is in terms of X and D?
Square root of x squared plus d squared.
That's the magnitude. How about the vector?
Oh,
Sorry, what is
x.
I had minus J, but how much I had?
X
Yeah,
minus,
an X amount in the I had direction and?
minus d.
But it's negative, right? A D amount in the J hat direction.
Yeah.
So think about vector R1 again. It takes you from here to here. So it takes you to the right, X, and then it takes you down. So we're going to write E1. So by now, you should tell me which form of the electric field, the one that involves R cubed or R squared? Cubed, because the unit vector, this one is even worse than the 45 degrees, right? It's not clear at all. So you need to, so it's not so obvious to write the unit vector. So I would go with this one. So K, Q1, and then R1 cubed, and then R1 the vector. K is K, Q1 is Q, okay? I would worry about the R cubed in a second. And then we all said R1 is X I hat plus minus D J hat, right? D J hat. Now what's the magnitude of R1? R1 will have, you will square this, add them, right? Take the square root. So it's going to be X squared plus D squared square root, right? Square root. So what would R1 cubed be if I do R1 cubed? If I cube this vector, what do I get? To what power? It's going to be X squared plus D squared to the 3 halves, because the square root is to the 1 half. So when you cube it, you get to the 3 halves. It will be to the 3 halves. Okay? So you will have X squared plus D squared to the 3 over 2 power. Let's make this one a little nicer. Okay. So that's E1. Okay. Let's do the next one. Let's do E3, because let's get the harder ones out of the way, and then we'll do E2 because it's the easiest. So let's do E3. The cube or the square? Which one? The one that involves the cube. Because the vector pointing from this way, we don't know what the unit vector is. It's not easy to determine. So I put K, C1, R3, Q, R. You get K, Q. Is the distance, is R3 more than R1 or the same as R1? The same. So that distance is the same. So this bottom part is going to be the same. Yes. Yes. Did I? Oh yeah. Should say. Okay. Yeah. Thank you. Now, what's the vector? This vector.
X,
Okay, yeah, so R3, you said is what? X I hat plus D J hat. It has to be plus, right? Because it takes you right and up. So yeah, X I hat plus D and J hat. And finally, E2. It's going to be K, Q2, R2. In this case, the squared or the cube? I think the squared makes the most sense because what's R2? The unit vector that points from Q2 to this way, yeah, it just points to the right, which is an I hat, yeah. So let's put, so K and Q, Q2 is Q. And what's the distance? Just X, yeah, so X squared.
Square.
And then you said I hat, right? Yeah. And then, so we want the total. We want the total, so we will add all of them. Add them. So if you add 1 and 3, let's add 1 and 3 first because something nice happens. What happens there? Yeah, look, they have everything the same, but except this one is plus, this one is minus. So the J hat stuff cancels. No more J hat, which agrees with what we said. We expect the field in total to just point in the X direction. So the J hat goes away, and so we just add these. This one just doubled, right? The X and the X, you would have twice the X. So you have twice, so it would just be K, Q, and then 2X, and then this stuff on the bottom. So you have the K, Q, and then 2X. So I'll just put X and then 2. And then you have X squared plus D squared, and then 3 halves power. And then plus this one, which is K, Q, over X squared. And everything involves an I hat, so I hat will just be factored. And that would be the answer. So it matches our expectation. It just would be to the right. And then we're going to the next one. Okay. Next one will be what's called a dipole. And we'll just introduce it without saying the name dipole, but I just said, okay? So we're going to, it's a plus and a minus charge. Instead of having 3 pluses, we just have 2 pluses. I'm sorry, 1 plus and 1 minus. That'll be one. Next one. Can I erase this left board?
Kenapa di sini kecil?
Okay.